welcome to this video tutorial. This is the fourth in our series of videos to help you get started with Kubernetes. These videos give you practical demonstrations to help you containerize your applications and deploy them with Scaleway Kubernetes Kapsule. In this video, the fourth in the series, we will focus on storage for your Kubernetes cluster. So we'll very briefly recap the first three videos of the series before diving into the topic of storage. First, we'll look at why we need storage and how storage works with Kubernetes Kapsule, including the very important concept of a stateful set. Then there'll be a practical demonstration during which we show you how to add persistent storage to a cluster using a stateful set. I'll briefly touch on how you can go further by talking about snapshots, and finally we'll sum up the key takeaways at the end of the video. So as I mentioned, this is the fourth in our series of videos about getting started with Kubernetes. Let's quickly recap the first three to make sure we have the right foundations for this video. The first video showed you how to use Docker to containerize a simple application. We walked you through the process of creating a Docker file, building an image, running the application from the image, and then pushing the image to the Scaleway container registry. In the second video, we showed you how to deploy that containerized application with Kubernetes. We created a Scaleway Kubernetes Kapsule cluster, installed kubectl on our local machine so we could connect to the cluster. We pulled the application image from video 1, and finally we deployed the containerized application to the cluster. In the third video, we created a YAML manifest to specify a load balancer service. And again, we used kubectl, this time to deploy our load balancer from the manifest, and we saw how the Cloud Controller Manager created and configured a Scaleway load balancer with an external IP so that the cluster was accessible from the public internet. This is what our cluster looked like at the end of the last video. For the purposes of this video, we assumed that you've at least followed videos 1 and 2, so you should have created a Scaleway Kubernetes Kapsule cluster and configured kubectl to manage it. If you don't have a load balancer or a deployed application, you'll still be able to follow this video. Before we start with the practical demonstration, let's first look at some fundamentals about storage and ask ourselves why we might want or need to add storage to a Kubernetes cluster. So first, let's go over some key concepts. We're going to differentiate between a Kubernetes system volume and a persistent volume. So a system volume, first of all, is used by the Kubernetes system itself to store its essential files that keep everything running correctly in the cluster, like runtime binaries, configuration files, and certificates. These volumes are managed by the Kubernetes nodes, and they're ephemeral in the sense that they live and die with the node. In fact, we can see these system volumes in the Scaleway console, so let's just take a look. So here in the instances section of the console, we can see the three nodes of our cluster. I think I originally started with one in an earlier video, but I've scaled up since then. And here in the volumes tab, we can see the three attached volumes, so they're linked to each instance, each node of the cluster. Each one of these volumes was auto-created when we created the cluster, and we really don't need to worry about them, and we shouldn't attempt to use them. So if we go back to the slides. So as we said, applications in our cluster can't use the system volume to retrieve or store any data, and this is where persistent volumes come in. These can be used by the applications running inside a cluster to read and write data. And these volumes store data in a way which persists beyond the lifetime of a single pod. They don't get deleted if a pod does. Unlike the system volume, persistent volumes aren't automatically created. You need to provision them, and we'll see how in just a minute. So what kind of applications need to use persistent storage? That's where the difference between a stateless and a stateful application comes in. Stateless applications, here on the left, do not load or save data at any point. So each request to a stateless application is independent. There may be data in the payload of the request, but no previously saved data is used. So a typical example of a stateless application would be a microservice or the Who Am I application we saw in the previous video that just prints some information to the screen, or a search engine, or a request to a search engine. In fact, containers were originally built to be stateless, hence we have written here original Kubernetes, but as the usage of containers has increased, the idea of containers and Kubernetes itself has had to adapt to incorporate statefulness. Which brings us to stateful applications. So these do retrieve and store data, and most applications today are stateful, like all databases are stateful, online banking with all your transaction history, online shopping with all your previous orders and remembering the contents of your cart. In order to run stateful applications in Kubernetes, we need to provision persistent storage volumes where these applications can store the data that gives them their state and retrieve it whenever they need. So how do we provision storage for these applications? Well, cloud providers such as Scaleway provide a CSI or Container Storage Interface Provisioner and default storage classes that their managed Kubernetes products like Kapsule can use. So these describe the classes of storage that the provider can offer for your cluster. And Scaleway provides block storage as its storage class, meaning we offer persistent storage for our Kapsule clusters via our block storage product. Little like how in the previous video we created a load balancer service in our cluster, which corresponded to the Scaleway load balancer product in the console. Dynamic volume provisioning or dynamic storage provisioning allows you to create storage volumes for your clusters on demand. So you just describe the storage that's required. We're going to see how to do that in just a minute. And then this is automatically provisioned by our container storage interface. Note that if you are a more advanced user, you can also create your own storage classes to specify custom storage and or custom parameters. I'll put the link to the doc in the description below for this, but it's outside the scope of this video. One thing I'll mention is that Scaleway has upgraded the block storage that our storage class uses. Previously, our storage class was Scaleway BSSD, whereas now it's SBS with some different subtypes. This new block storage offer is faster, offering better performance and lower latency for your read-write operations. The default option of SBS default will give you SBS 5K, but you can specify SBS 15K for even lower latency thanks to more input-output operations per second capacity. Now, in order to provision this persistent block storage volume resource in our demo today, which we're going to do in just a minute, we will use a persistent volume claim. And a persistent volume claim is a request for and a claim to a persistent volume resource. Persistent volume claim objects request a specific size, access mode, and storage class for the persistent volume. It may sound like an extra layer of complication, but in fact this makes things simpler for the user because the user can just say what they want without needing to worry about the details of how it's provisioned. So we've established that an application that is reading to and writing from storage is a stateful application. In our previous video, we deployed a stateless application using a deployment object in Kubernetes. And in this video, we're going to deploy a stateful application which requires storage. And for this purpose, we will use a StatefulSet object instead of a deployment object. Both deployments and StatefulSet objects manage the deployment and scaling of a set of pods with identical replications of a containerized application. But StatefulSets can also provision and manage persistent storage for their pods via PersistentVolumeClaims. And in order to ensure data consistency and synchronicity as pods read and write to storage, the pods have sticky, persistent identities. And you can see how it works here in this diagram. So you can see the relationship between a pod, which has a volume mount, a pod of the StatefulSet, linked to a persistent volume claim, which itself is going to provision the right persistent volume. It is possible to create storage for a Kubernetes pod without a StatefulSet. You could use a deployment and specify volumes for each container there in combination with a separate persistent volume claim object. But for the purposes of this demo, we'll show you how to do it with a StatefulSet instead of a deployment. So let's jump into the demonstration. Just for information, I'm using pretty much the same cluster as from previous videos. Let's just take a look. So kubectl is all configured. If we do a kubectl get all, we can see the deployment from previous videos and the load balancer service as well. And just to show you how we can check the storage classes that are available to us, with a kubectl get storage class, we can see that the SBS class that I talked about before. Okay, with a little ls, we can see the load balancer YAML file and the whoami deployment YAML file that we used to create the service and the deployment from previous videos. We're going to create a new YAML file called ss for StatefulSet.yaml, and this will be to create our StatefulSet manifest. So I've already prepared the text, we'll paste it in, and I'll go through it step by step. So just as we saw before in previous videos, the API version specifies which version of the Kubernetes API to use to create this object. Kind specifies the kind of object defined in this YAML file, so here it's a StatefulSet as opposed to a deployment or a service. The metadata helps to uniquely identify our StatefulSet object itself, so we'll give it a name, SSCSI-SCW, and the spec specifies the desired behavior of the StatefulSet, and there's a lot of subparts here, so let's go through them. We tell it to make 5 pod replicas. The selector field defines how the StatefulSet finds which pods to manage, in this case using that label that we just defined. The template describes the template for the pods that will be created. So we have the standard metadata like before, specifying the set of labels for the pod. The spec specifies the desired behavior of each pod. So previously we were specifying the desired behavior of the StatefulSet, and now we're talking about the pods. So we list the containers for each pod. Here we have just one, and it's named busy pvc scw, and we tell it to use the busybox image. This is a minimalistic, lightweight image with just a shell environment, and we're not really going to use this for anything. It's just an easy example for the purposes of this demo. We also specify a volume mount at location data for our storage volume, we're going to specify just after, called CSI vol Scaleway. Finally, we give a command to the container to sleep for 3,600 seconds or 1 hour, and this is just to keep it active while we do our demo so that it doesn't launch then shut down because it's not doing any actual work. So next we have the volume claim templates, and they have their own metadata and spec, and these define the templates for the persistent volume claims that the StatefulSet will create for each pod, which will then in turn themselves trigger the creation and management of our corresponding persistent volumes. So we specify the access mode. The volume can be read and written by a single node. The aforementioned storage class, so as we saw, we're going to use SBS default. And in resources, how much storage we want, 1 GB. So to summarize, we're creating a StatefulSet object with 5 replica pods running a lightweight container called busybox that's just going to sleep in the background for an hour. The StatefulSet will create a persistent volume claim for each pod, creating a 1 GB Scaleway block storage volume for each pod mounted at data. So let's just save and exit. So now we just need to tell Kubernetes to create the StatefulSet from that manifest we just created. And here's the command, kubectl apply, and we'll give it the YAML file as an argument. We can see that it says it's created our StatefulSet. Let's do a little kubectl get all to see what's happening. Okay, so we can see that our StatefulSet pods are creating up here, and this can just take a little while. So if we fast forward in time, okay, so thanks to the magic of video, I've sped forward and we can see that now all 5 of our StatefulSet pods are up and running. Let's double check these pods and their storage by taking a look at our Scaleway console. Okay, so here we're still in the volume section of instances where we were before. So these are our system volumes corresponding to our cluster's nodes. But if we go down here to block storage, we can indeed see that the CSI in our managed Kubernetes cluster has created 5 block storage volumes, 1 for each of the pods in our StatefulSet. And these storage volumes are linked to the instances that make up the nodes of our cluster. Let's go back to the command line. Just clear that for make easier viewing. And we'll see what happens to our block storage volumes if we resize our cluster to reduce the number of replicas to 0. And this should show us some interesting and important behavior when it comes to the block storage volumes of each replica pod. So I could go into the StatefulSet manifest, change the number of replicas to 0 and then do a kubectl apply, but there's a quicker, simpler way if we only want to change the number of replicas and nothing else. And that's with the kubectl scale command. So we use kubectl scale, StatefulSets, and then the name of our StatefulSet, which was SSCSI Scaleway, and we tell it replicas equals 0. And it says it has scaled. Let's check what's going on with a kubectl get all. Okay, we can see that this one here, number 4, is terminating. It can take a while for all replica pods to terminate, so let's just switch back to the console and we'll have a look at what's going on there. Refresh this block storage page. So we can already see that this block volume is detached from its corresponding pod. And if I use the magic of video to speed forward in time a few minutes and refresh again. Okay, so it's been a couple of minutes and I've refreshed again, and we can see that all of our block storage volumes are now detached because they no longer have equivalent pods. So we'll go back to the command line to confirm that. Kubectl get all. Yep, all of those pods are gone. Let's scale back up now by repeating the command in reverse. So kubectl scale StatefulSets, and ours was SSCSI Scaleway, and we want this time to tell it to give us 5 replicas again. So to scale up, it says it's scaled, a little kubectl get all, and we can see that first pod is creating again. And if we go back to the console, yes, we can see that this one and another one in that time has indeed automatically found its corresponding pod and is attached again. So the block storage volumes are reattaching to their pods, even though those pods were deleted. So all the previous data that was stored there is still available. This really exemplifies how convenient it is to manage storage for Kubernetes in this way, with a high level of automation to ensure that storage volumes and pods can easily find each other. I'll just do a final refresh. And yeah, all the volumes have reattached to their pods. In terms of next steps and going further, one thing you might want to look into doing next is to learn how to make snapshots of a volume. A snapshot is a consistent, instantaneous copy of a block storage volume at a certain point in time, and snapshots are useful for backing up data and facilitating data recovery. You can make a snapshot by creating a manifest for a volume snapshot object and applying it with kubectl, as we've seen for all our other objects, and then witnessing the snapshot appear in the block storage section of the console. I'll just show you where that would be. Here, next to our volumes tab, you can see that we have this snapshots tab. And the required manifest for a volume snapshot is very simple compared to the ones for creating a stateful set, for example. I'll include full details of this and also the documentation for creating volumes in Kubernetes from existing snapshots in the description box below. And that's it, we're done. Dynamic volume provisioning makes the creation and management of persistent storage with Scaleway Kubernetes Kapsule easy. In this video, we saw how to create the YAML manifest to specify a stateful set that included a persistent volume claim. We told kubectl to create that stateful set and those pods, each with their own accompanying persistent volumes, and we were good to go. We had the added reassurance of being able to see everything in the console. This was the last in our series of Kubernetes videos. We hope you enjoyed them. Don't forget to check out the Scaleway YouTube channel, the blog, and the documentation website for more Kubernetes resources. All links are in the description below.